Okay, so we're delighted to have Jordan Cotler from Harvard, who's going to be telling us about 5 lessons in de Sitter quantum gravity.
Great. Well, thanks so much for giving me the opportunity to speak, and it's nice to be back at NYU. So I'm going to tell you about some work over the last 5-6 years or so in collaboration with many co-authors. Let me in particular underline Christian Jensen, who has been my partner in crime for many of these investigations. And what I'm going to tell you about is a takeaway, a synopsis of lessons that we've learned in trying to make sense of de Sitter quantum gravity. Now, let me say this as a preface. Feel free to ask any questions that you want during the talk. This is intended to be somewhat pedagogical, with an emphasis on somewhat. No. And what I'm going to do is explain to you a particular example of de Sitter quantum gravity that will explain each of these 5 lessons in turn. And the idea is that these 5 different principles will be useful not just in toy models of de Sitter quantum gravity, but for example, in 1+1, where we'll spend most of the time of this talk, but also in 2+1 and ultimately 3+1 dimensions where we live. So we, at least nominally, live in something like asymptotically de Sitter space, positive cosmological constant. So it's of great importance that we understand de Sitter quantum gravity to better calibrate predictions for our own universe. Let me first preface this with some conceptual picture. So we're very used to, in the context of ADS-CFT, this is the Penrose diagram for example, an eternal black hole, that we think in ADS-CFT about the conformal field theory living at the boundary here at space-like infinity. Maybe here there's 2 CFTs. And we're used to having, on the one hand, a CFT, which is quantum mechanical, be dual to a theory of quantum gravity, which is in turn quantum mechanical, and we have an emergent dimension of space. In de Sitter space, so de Sitter space looks superficially similar in terms of its Penrose diagram. But now, conformal infinity is actually in the past and in the future. So this is future, and this is past. This is de Sitter. And at least in the context of de Sitter holography, which is still in its nascent stages, that one expects that up here we have something like Euclidean CFT, which in fact is non-unitary, which is to say that if you Wick rotate it into a Lorentzian theory, that it's not a unitary Lorentzian theory. And perhaps we have another copy of Euclidean CFT down here, which is somehow supposed to be dual to de Sitter quantum gravity with quantum mechanics and space and time. So whereas in ADS, there's an emergent dimension of space across the duality, in something like de Sitter holography, we might expect that there is an emergent dimension of time, that this Euclidean CFT intrinsically does not have time within it, and that the dual theory does have time. Moreover, because the Euclidean CFT doesn't have time and is moreover non-unitary, it's the case that it's not just that time is emergent, but that quantum mechanics itself would have to be emergent. Indeed, it's hard to conceive of quantum mechanics in the absence of time, and there's a precise sense in which one would expect something like DS-CFT to have to contend with issues of emergent time. That being said, I'm not going to propose a particular example of DS-CFT in this talk, although near the end I can allude to some progress in that direction. But our focus is going to be to make sense of the gravity path integral. That is, to think about something like Einstein gravity or some lower dimensional model in the context of Feynman's path integral, and see what traction we can have in computing perturbative and non-perturbative amplitudes, which will elucidate the structure of what we mean by the bulk quantum gravity theory and provide clues as to what the boundary holographic dual might be like and what properties it might have. So the main hero of our talk, or the main subject of our talk, is going to be de Sitter JT gravity, or nearly de Sitter JT gravity. Which is a 1+1 dimensional theory of gravity. And we're not studying this because we have some particular affinity towards 1+1 dimensions, but rather because this is a toy model, which is going to be instructive for higher dimensional investigations. First, let me give you the setup of this nearly de Sitter JT gravity theory. So let me cordon this off. So the action of the theory is as follows. The action is S naught over 4 pi times pure Einstein term. So this is essentially going to become an Euler characteristic because we're in 2 dimensions, plus a bulk term, which is like this. So let's unpack this action. So the first term that we have here is equal to minus I times the topological Euler characteristic. The reason that you get a minus I is because usually we define this geometric instantiation of the Euler characteristic in Euclidean signature, but if you do it in Lorentzian signature, it turns out that you'll pick up an extra factor of minus I. This minus I, by the way, is useful, just as a remark, because when we want to think about this in the path integral, the object that we're really going to look at is, the integral over fields with respect to e to the I s times the JT action. So as such, this is going to basically give us, this is going to contribute a term, which is going to be like E times the Euler characteristic times S naught. So it's like a genus counting parameter.
But what's the Euler characteristic of pseudo-Riemannian manifold? Because now we are in Minkowski, right? So
yes. So let me return to this in a moment. But so for example, think about the Hartle-Hawking state, which we'll talk about more what this is in a moment. So the Hartle-Hawking state you can think about as being a deformation, or it's a complex time contour which is deformable to the minus signature Euclidean ADS disk. So what I'm saying is that if you take that metric and you plug it into here, you'll get minus I times the Euler characteristic of the ADS, Euclidean ADS disk. But we'll see why that's a sensible thing to do at the moment.
Yeah, for example, for the sphere, you wouldn't have that because it's no so it will reverse, right?
Let's return to the question of the sphere in a bit. We'll come to that. So the way we're going to architect the talk is that we're going to mostly talk about global de Sitter and think about fixed topology, and then we'll talk about other topologies in a moment and address those concerns. So we'll return to that. So, but for this term here, so we have here a non-dynamical dilaton, which serves as a Lagrange multiplier, which when you integrate this out, sets R equals to 2. So it's integrate. We're going to integrate over the metrics of constant positive curvature. It's in this sense that we're considering that it's like de Sitter as opposed to anti-de Sitter. Now I also need to supply you with the boundary conditions that we will impose on the fields at asymptotia, because this is just the bulk contributions. There's also a boundary term. Well, we could talk about that later. But the asymptotically de Sitter boundary conditions is that as t goes to plus or minus infinity, that is, you consider times in the future, far future versus the far past, you have minus dt squared plus e to the plus or minus 2 pi t times d theta squared, where theta goes like theta plus 2 pi best. So this is a periodic direction. So these are the asymptotically de Sitter boundary conditions. And then on the dilaton, we're going to impose that the dilaton goes like plus or minus e to the plus or minus t. So here we see that there is a single free parameter in this theory that demarcates the asymptotic data, which is the value, the renormalized value of the dilaton near asymptotia. So we can think about this as this phi basically labels the boundary conditions. So for people who are perhaps more familiar with thinking about the higher dimensional version of this in which it's reorganized. So in higher dimensional gravity, when you do a Fefferman-Graham expansion, you fix, for example, the leading behavior of the metric, and then you allow the subleading behavior to fluctuate. You can think about fixing the leading behavior of the metric is like fixing the, it's like fixing phi. This is like fixing the leading asymptotic data. So we'll see in the quantum mechanical picture that our asymptotic states are going to be labeled by fixed values of phi. All right, so with this in mind, let me first tell you what the classical solutions are to the theory before we embark on the quantum mechanical picture. So let's look at Lorentzian solutions because we're interested in dynamics and Lorentzian time. So we want Lorentzian solutions that satisfy these equations, the ensuing equations of motion, and moreover, that satisfy the asymptotically de Sitter JT boundary conditions. So it turns out that there is a 2-parameter family of such solutions, and let me tell you what they are. So the solutions are look like this. Where we can, where f of t is some function that, let me plot it out. One can do some gauge fixing, but you want it to smoothly go from 0 to some parameter tau. I'll tell you what this is in a moment. So this looks a lot like global de Sitter space. The way you should think about it is as follows. Oh, sorry, let me write down. So this is the metric part, and then I have to tell you what the dilaton is. The dilaton is phi over 2 pi times alpha singed t. So this is the space of solutions. So how should we think about this? So let me draw a picture of global de Sitter space. Like this. So the idea here is that we see that alpha, so there's two parameters that describe this, at least for the metric degrees of freedom. So for the metric degrees of freedom, we have alpha and we have tau. So what alpha is that we're considering spacetimes that have a bottleneck of circumference 2 pi alpha. So it turns out that in the 2D theory, you can vary alpha and you still satisfy r equals 2. There's also another parameter tau. So let me say alpha is in, so this is the bottleneck parameter, and this can range in the positive real numbers. And then we also have a twist parameter tau, which is identified with itself mod 2 pi, where you can think about the twist as relating a point on the upper asymptotic boundary with a point on the lower asymptotic boundary, and that the change in angle is tau. So there's a twist parameter.
So it doesn't appear in the metric explicit, or is it like a modular parameter?
Well, it is in the metric in the sense that it's in this f prime of t. So this f prime of t is the thing that induces the twist. Yes.
So is this capital phi the same as the capital phi in a boundary condition?
Yes.
Then why doesn't our boundary condition fix the value of alpha?
Good. So right. So what you'll see is that let's return to that in 1 second.
Okay.
I'll show you. Good question. So one observation is that the classical solutions are ones for which yeah, good. So the classical solutions are ones for which the phi in the past equals, okay, so there's an issue of orientation, but roughly speaking, the phi in the past equals the phi in the future. So past and future. So we see that the sinh, roughly speaking, goes from minus, so actually, we can absorb this into the definition of phi. That's really the right thing to do. Then phi runs from minus phi in the past to phi in the future. So the on-shell solutions require that the boundary conditions here and here have to equal one another. All right, so these are the classical solutions. So now let's actually turn to quantum mechanics and ask, what is it that we actually want to compute in this theory?
So now, how many parameters we have? We have phi, that's the capital phi, that's it's fixed by the boundary conditions.
Yeah. Yeah, so for any fixed phi, we can vary, we have alpha and tau is essentially the phase space. And in a certain sense, they're conjugate parameters in the phase space. So two-dimensional phase space. All right, so again, this is the bottleneck and this is the twist. All right, so what are the quantities that we want to compute in de Sitter? So let me draw a picture that is that summarizes the first lesson, which is that meta observables in de Sitter are matrix elements. So let me pose this to you as a question. Suppose I give you the gravity path integral for de Sitter JT, or any de Sitter gravity theory, and I ask you, what should we compute with it? Well, the answer is that you might want to compute something like the wave function of the universe, or more generally S matrix elements, which is to say the following. Suppose you prepare some number of boundaries in the past. So let me, draw them like this to suggest that they're going to go upwards. And maybe I specify in this case some boundary data, like I say we're phi 1 prime in the past, this is phi 2 prime, and this is phi m prime, for example. That something happens in the middle that we don't know. And then in the future, we end up with some asymptotic boundaries, for example, like phi 1 and phi 2, for example, maybe up to phi n. And what we might want to do in the path integral is sum over all of the different ways that we can go from this configuration to this configuration. So for example, a contribution here might include one where, maybe this one goes to the second one, maybe this one goes to, maybe these two merge and have some genus and then become this one. These are the kinds of amplitudes that we want to compute using the path integral. So let me begin with the simplest example of how to compute this, where we'll just consider the one-to-one process. So the one-to-one process is the one where we are going to start with just one boundary in the past that has data phi prime and end with one boundary in the future with asymptotic value phi. We're going to figure out all of the ways that we're going to fill in this geometry. So let me make another comment. How should we interpret this quantum mechanically? The words that we want to say is we have an S matrix. And the path integral is computing for us S matrix elements. So in the past, for example, we have a multi-boundary state, which is phi 1 prime through phi m prime. And in the future, we have a boundary state, which is phi 1 through phi n, like that. So the idea is that the path integral is computing for us the transition from m boundaries with this boundary data to n boundaries with this boundary data, and we're summing over all of the possibilities in between. So in this case, we're going to consider just the cylinder contribution. So let me write out what this is in this notation. So we have phi in the future and an s and phi, and we're going to look at this particular this contribution, which is the leading contribution in the genus expansion for Lorentzian geometries. And we're going to study this first, and then we can consider the higher genus amplitudes thereafter.
And why do you want to do that? Because, for instance, if you say, well, I do canonical quantum gravity, then you have a foliation in time, and then you only have that diagram, right? And nothing else.
Yes. So this is related to the following problem. It's that well, you also have possibly crunch geometries, because you can have smooth data that if you evolve it backwards will terminate in a crunch, and we'll have to encounter that shortly. But relatedly, another way of rephrasing what you're saying is that the only globally Lorentzian geometry in 2 dimensions is this geometry. That if you wanted to consider something of higher genus, there's actually no way of having a smooth Lorentzian geometry that's not just a disjoint union of cylinders. That's globally Lorentzian and non-singular and has constant positive curvature. There's no way of arranging for that. So we're going to have to deal with that issue later on. But for now, that's why this is the most natural thing to study first for that reason, because it's conceptually the easiest. Even the Hartle-Hawking state, of course, this is another geometry that only has a future boundary, is really a complex metric. It's not actually globally Lorentzian. So that will be under the purview of these other contributions, which are going to correspond to complex metrics in some particular but controlled fashion. So let's study this. Erase some importance for now.
Here, the boundaries are asymptotic boundaries. So you cannot take finite boundaries.
That's right. Yeah, these are asymptotic boundaries, exactly. So what we're going to do is we're going to try to compute this amplitude. And since I want to emphasize some conceptual aspects, let me sketch how the computation works. And then we can talk about, we're interested in what the result means and how to interpret it physically. I'm happy to tell you more details of the computation, but I'm going to sketch it for you. So suppose again that we have this boundary in the future phi. We also have phi prime in the past. It turns out that there's a nice decomposition that you can do in JT gravity, where you can cut the global de Sitter spacetime at the bottleneck. You can consider trumpets where, let me write this, so this is 2 pi alpha. The idea is that we're going to want to have a trumpet that goes from phi prime to a bottleneck of circumference 2 pi alpha, and another trumpet that goes from 2 pi alpha to a different phi, and we're going to want to glue them together by integrating over alpha, and also over the twists. The twists are sort of easy to deal with. So schematically, we want to compute something like this. And the way that one can write this in a slightly more transparent notation is that we have this integral. It turns out that the right measure that you get is d alpha squared. I'll explain. And then you have what's called a trumpet factor, which brings us from, so let's actually call this one pi prime. So this brings us from a bottleneck of 2 pi alpha to a future asymptotic boundary, which is phi prime. And then we also have zt tilde star, which brings us from alpha to phi. So that's so phi to alpha. And then we're going to glue these together and integrate it over twists, which just will give us a factor of 2 pi. And it turns out that in GT gravity, one can compute these quantities and they're one loop exact. There's a localization argument. Let me just tell you what the answer is here. It ends up being root I phi over root 2 pi times e to the I alpha squared phi. This is the one loop example. This is the one loop answer, which happens to be one loop exact. And when you do this integral, what you find is, let me just write out part of the answer. E alpha squared
Sorry.
over,
What does determine the measure?
I'm sorry?
The measure, the iteration measure, right? The alpha square and the alpha.
So
Has to be invariant under something.
yeah, so essentially the integration measure is really d tau d alpha squared, because so one way you can get this is that there's a few ways of deriving this answer. One is that you can write down the symplectic form for the theory for the phase space. You can look at the Fathian of the symplectic form, which will give you the measure over the in a phase space quantization. And what you find is that the measure is d tau d alpha squared. I've here already integrated over tau because it'll just contribute a 2 pi out front. I've already absorbed that into the definitions of the z tildes. But the short answer is you can derive the measure by figuring out the symplectic form on the phase space of solutions, and that will give you the measure by taking the Fathian.
But wouldn't that be only a semi-classical expression that will have corrections? I suppose S0.
Well, so one way you can also think about this is that, so think about this also in the Euclidean ADS case. So you can think about what is the space of constant, or say, it turns out to be similar in the case of constant positive curvature, but constant negative curvature metrics on the cylinder. Because we have to do, they have to be constant curvature. There's a moduli space, which is the Weil-Petersen moduli space. The Weil-Petersen moduli space has a natural symplectic structure on it, and from the symplectic structure, we can derive essentially the measure over the moduli by taking the Fathian of the symplectic form. That's another way of getting this. It's a similar analysis also in the Euclidean ADS case. No.
Is there a matrix model in this case? Because like you said with the negative curvature, there's a matrix model here.
So let me unpack that question. So it's known due to Sodchenker and Stanford that there is a matrix integral, at least a formal matrix integral, topological recursion, which describes Euclidean ADS amplitudes and in JT gravity. So Euclidean ADS.
Yeah.
So it turns out that the answer is that there is, I can mention this at the end, there is a topological recursion that will describe the higher genus amplitudes, but it's not really a matrix integral for an interesting reason. Okay. So let's come back to that.
And sorry, when you do either symplectic or Keller quantization, you have sometimes to decide whether there is a metaplectic correction.
Yes.
So here
we're going to we have no additional correction, but there's a few different ways of seeing why that would be natural. One is that you can also do the quantization in the BF language, and in the BF language you don't. There just is a canonical symplectic form that won't have that metaplectic correction. Okay. In any case, so the other thing that I need to mention is that phi, that for this integral to converge, something I swept under the rug, which I'm going to mention now, is that there needs to be an I epsilon prescription. And I'll just tell you what it is. It's that phi in the future, let's see, did I get this in the wrong order? Yeah, that's right. Good, this is right. So that phi needs to be real plus I epsilon, and this is real minus I epsilon, depending on whether the boundaries are in the future or in the past, so that this integral converges. And then the answer that we get, which I'll circle, let me maybe just write it down here, is phi x phi prime is I over 2 pi times root phi root phi prime over phi minus phi prime. And I'll put in the I epsilon for bookkeeping. So if we do this integral, we just get this answer. So this is the answer for the one-to-one amplitude. Okay, great. So what does it mean? So this is just some function of phi and phi prime. Why do we care about it? What does it tell us about de Sitter quantum gravity? And what should the interpretation be? Now, I want to point out something important in this calculation that we don't often think about in the Pathfinder world, but we need to be very careful of, which is that if we want to assess what this amplitude means, we need to understand what is the inner product on these asymptotic states. In other words, a piece of data that we don't a priori know is if you take, for example, two states in the future, phi 1 and phi 2, what is their inner product supposed to be equal to? In a way, it's tempting to imagine that they're just L2 normalized states, that they're kind of like position states, for example. But in fact, in order to interpret this amplitude, we need to know whether, in fact, they have a non-trivial inner product, because if they do, we need to correct for it. In other words, if we want to assess something like whether or not this amplitude is unitary, we definitely need to know what the inner product on asymptotic states is to understand what the resolution of the identity ought to be. So that will bring us, so we now need to do a computation of the inner product in asymptotic states, and let me now tell you how to compute it. So that brings us to the second lesson. I'll say what this means is that the inner product on asymptotic states ends up being a path integral over asymptotic metrics. So what does that mean? Let me draw you the picture for this. So let's think about what the space of asymptotic metrics looks like. So as t goes to infinity, the asymptotic metrics are as follows. They look like ds squared is minus dt squared plus, after the coordinate change, e to the 2t plus alpha squared plus dot 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 d theta squared. So all I've done here is I've just taken my global de Sitter solution, I've just expanded it for large t and then done a field redefinition of t, or just a shift in the t coordinate. So here, this alpha squared is not really alpha squared. This is just what it is for the global solution. But really, we should replace this with a constant, and I'll call that constant p. This is just the subleading constant in the expansion of the asymptotic metric. So let me maybe in parentheses say that it used to be alpha squared, but it's really some parameter p. So let me make an observation here.
So it means that if you compute asymptotic charges, it will be alpha dependent.
Yes. So, but the observation is that in the limit that t goes to infinity first, because we're looking at a surface that's really far in the future, this subleading fluctuation can take either sign. This parameter p can be positive or negative. Now, in the case of the global de Sitter geometry, when this is alpha squared, okay, that if you take the global solution and expand it at asymptotia, this alpha squared has to be positive. But abstractly, when you do the analog of the Spefferman-Graham expansion for the asymptotic data of the metric, in the limit that t goes to infinity first, the subleading fluctuation is not constrained to be positive. It can take either sign, because it being negative will not be able to dominate this e to the 2t term, which is going to infinity. So the picture, just to draw the following picture, is that what we want to try to compute is near asymptotia, this t goes to infinity, is you want to consider a surface that's at phi, where we have the dilaton be phi prime, and another surface where we have it be phi, and we want to take the limit as the amplitude as these two phi primes approach each other and also go towards infinity. So the logic of this is as follows. Recall that in ordinary quantum mechanics, if you want to compute the inner product of two states, you can consider their transition amplitude in the limit that the time of the transition amplitude goes to 0, because then you're just looking at the inner product between them. So the logic here is that as you take these two towards infinity and you take them to coincide, there's a path integral computation that will give us the inner product between them. And what's interesting is that in quantum mechanics, like for just a single particle, that path integral is trivial. But here, actually, there's non-trivial moduli, it turns out, that you have to integrate over in order to compute the inner product. So I can walk through the computation, but in the interest of time, let me tell you what the answer is. So actually, let me show you the formula and then the answer, because the formula is somewhat illuminating because I wrote this formula out. So it turns out that if you work through it, what the computation ends up giving you is that the inner product on asymptotic states looks a lot like the one-to-one point, the one-to-one amplitude, but with a difference. The difference is that you integrate over parameter dp, but instead of it so d alpha squared was integrated from 0 to infinity, but here you integrate from minus infinity to infinity because this p parameter can asymptotically, this is the space of asymptotic metrics, can be positive or negative. Now, if p were to be negative, that if you set that asymptotic data and evolved it backwards, you would end up in a Milnor singularity. You'd end up in a crunch geometry. But that's still okay in terms of asymptotic data. There's nothing wrong with that asymptotically, just at finite time. So in any case, so this integral over dp of e to the I p phi minus phi prime, so it looks basically just like the other integral, times these factors of root phi prime over 2 pi. And what does this equal? So the answer is that this inner product is root phi prime times delta of phi minus phi prime. I won't box this. So what we see from this calculation is that the asymptotic states are almost delta function normalized, but they have these extra square root factors. And if this is a less familiar way of computing inner products and asymptotic states, there was a recent beautiful paper by Maxfield and Held, where they did a quantization of de Sitter JT gravity in the canonical framework, and they reproduced the same answer. So if you want to do it in canonical formalism, you'll also get the same answer when dealing with the same subtlety. So there's different routes of getting this. So that's the second lesson. Okay, so now we're cooking because oh good. So let me make one quick comment. So you might ask, if you fix P as asymptotic data and you evolve it backwards, what metric would you get? This is related also to your question from earlier. So let me write this out. So the metric, if you fix P and evolve backwards, is minus dt squared plus P cos squared of t d theta squared for P greater than 0. That's like when P is playing the role of alpha squared. But when P is less than 0, the metric that you reconstruct ends up being plus absolute value of P times sinh squared of t d theta squared. So if you choose a negative value of P, which is fine asymptotically, if you evolve it to finite time at t equals 0 in these coordinates, you're going to run into a Milnor singularity because sinh squared is going to vanish, goes to 0. So it's a space-time that crunches at t equals 0. And okay, good. All right. So what? So how do we put this all together? Well, let's put together this result with this result. So what it's going to be natural to do here is to take these phi's and to normalize them differently, divide them by I times, the I is just the pure phase, this just convention, divided by this root phi, so that now they become delta function normalized. And what answer do we find? The answer that we find, as you can see by staring at it, is actually quite simple. Is that phi, the transition from phi prime to phi, where I've done this renormalization, I've just redefined what I mean by phi here. It's just the same answer that we had before, but now where we strip off the factors of root phi on top. Okay, so it's just this divided by phi minus phi prime plus I epsilon. So this is our result. So let me make a few comments on it before we unpack the physics. Note that it has a pole when phi equals phi prime. So that is nice because recall I told you before that the on-shell solutions satisfy phi equals phi prime. So we're seeing that this kind of looks like a propagator where we have a pole for the on-shell solution. That's a nice feature. But in fact, if the Fourier transform part of our brain starts to salivate when we look at this, because we realize that this is just the Fourier transform of the Heaviside step function. In particular, if I were to define conjugate states to these phi. So if these are position space, you can define their Fourier transforms, which are like momentum states. It turns out that, okay, so let me just write the answer. If you work in the conjugate basis, what you find is the very simple answer that I'll label them by P. It turns out that the conjugate basis is directly related to this P parameter. You find the transition amplitudes are simply a step function P minus P prime, like this. Okay. Great. So how should we interpret this? Well, first, what it means is the following. It means that if you set in the past asymptotic boundary a positive p-value state, that it will sail on into the future, it will bounce, and it will land up in a future asymptotic state. In other words, if p is greater than 0, this amplitude is just 1. So it's unitary, but in a silly way, because nothing happens. That's also kind of compatible with the idea that in pure gravity, there's a sense in which h equals 0. There's no Hamiltonian. I mean, it's consistent with that intuition. However, what if p is less than 0? If p is less than 0, then the S matrix element is 0 because of the step function. So how should we interpret that? Well, what happens actually is that what a negative p corresponds to is a crunch geometry. Now, actually, this crunch geometry at t equals 0 violates the equations of motion. It violates this constant positive curvature condition that r equals 2 due to the presence of the singularity. So this crunch is really not in the space of bulk geometries. It corresponds to perfectly fine asymptotic data, smooth asymptotic data, but it leads to a crunch which violates the r equals 2 condition at finite times. So what we see is that what's happening is that crunch geometries, which are perfectly fine as asymptotic data, die out. They're projected out of the S matrix evolution. And they lead to a crunch, but those crunches are effectively annihilated and are not able to enter into asymptotic data in the future. If you start with the crunch geometry and something that will lead to a crunch, it will not survive into the future. So one notable feature of this that might be concerning to you is that this is not a unitary amplitude. It's not unitary because half of the states are dying off. So why is this the case? What does this mean? So there's two possible ways of thinking about this. One of the ways of thinking about it is to say, well, maybe we're supposed to look at higher genus corrections of the spacetime. Maybe there's other processes which we didn't account for, like a universe branching off or some higher genus contributions, which would restore unitarity in totality, because this is just a matrix element at fixed topology and fixed genus. This is just a subset of the actual S matrix element. But I'm going to propose that there's actually a different way of thinking about that. So that's a logical possibility, but let me mention a different piece of structure that's illuminating as to why this is a projector.
This will be an S0 dependent solution.
Yes, S0 in this case would be equal to 0 for the cylinder. I'm sorry, I mean, the Euler characteristic is 0 for the cylinder.
No, but I'm talking about the possibility that higher genus correction will restore unitarity.
Absolutely. So that
It will depend on S0.
it'll depend on S0. So it's plausible that, so it seems that there's really no way for that to happen if they're stratified by genus.
Yeah.
Exactly. There's a subtlety about what can happen for doubly non-perturbative effects where let's not talk about that yet, but exactly. So that's why that's not a plausible mechanism. So let me now tell you about the third lesson, which is that evolution in expanding cosmologies can be isometric. So this will provide a way of understanding why this might be the case. So let me draw for you a picture. Just keep an eye on the time, we're doing fine. So again, here's our picture of global de Sitter, like this. And in the middle, I'm going to draw our bottleneck as usual. And let me do the following. I'm going to write down the asymptotic Hilbert space. That's the one in the far past. So this looks like L2 of R. And there's also an asymptotic Hilbert space in the future, which also looks like L2 of R. And in the middle of the bottleneck, there's actually a Hilbert space associated with this. I'll call this H bulk, which you can think about as the states which at finite time label the bottleneck. And these are states which only allow the bottleneck, or alpha squared, if you will, to be positive. So this actually corresponds to L2 of R plus, because the bottleneck at finite times has to be positive. So here we can think about a map from this Hilbert space to this. So from the asymptotic Hilbert space to the bulk Hilbert space, and from the bulk Hilbert space back to the asymptotic Hilbert space. So that is, I'm saying that there's some amount of evolution here I'm going to call V dagger, and then there's another evolution here I'm going to call V. So V is a map from the bulk Hilbert space to the asymptotic Hilbert space. So let me write that out. So V is a map from H bulk to H asymptotic. And moreover, it satisfies the following property. You can check. So what is this V? These V's we've encountered earlier. They're these trumpets essentially. These are maps that bring you from bulk data to asymptotic data or backwards, depending. These are the matrix elements of these V objects, if you will. So what do you find? Well, you find that V dagger V is the identity in the bulk Hilbert space. And that, okay, so hold on. So what's going on? This map is a map from a smaller Hilbert space to a larger one. Now, they're both infinite dimensional. But what I mean in the infinite dimensional case is this is a map which is injective but not surjective. If they were finite dimensional, you would say that V, if it satisfies this condition, is actually an isometry, something which is used, for example, in the theory of error correction codes. Now, an isometry satisfies the feature that if you go from, so let me explain this direction of composition. If you go from small to large back to small, you get the identity matrix on the smaller Hilbert space. But if you go the other direction, if you go from large to large, what you get is a projector onto the subspace of the larger Hilbert space that corresponds to the bulk. Now, what's interesting then is that, let me point this out, this composition is precisely what the S matrix is, at least at this fixed topology. So let me circle this. So indeed, one can show that V, in this case, satisfies these two conditions. It's an isometry as opposed to a unitary. And that tells us why the S matrix has to be a projector. It's because isometries have this property that when you compose them from large to large, it forces you to have a projector onto a subspace. And that is actually precisely why we're finding that there's a projector here. Yes?
Is it clear that there's like a canonical isomorphism between the past asymptotic Hilbert space and the future asymptotic Hilbert space? Or
well, one way of understanding why there's an isomorphism is because there's an the boundary conditions are related to each other by t goes to minus t. Now you might ask, so in other words,
that's different because like that's just not same time evolution, right? Or
so the idea is that what the Hilbert spaces are, the past data and the future data look the same up to this issue of t goes to minus t. You can separately compute the inner product on those states, and you can figure out that they're a Hilbert space, which is L2 of R. There's separately a map, which is the time evolution map, which provides another map between them.
yeah.
It's actually not an isomorphism because it's projector issue.
Yeah. Okay.
Great. Okay, so very good. All right. So that's what I wanted to say about this so far. So that's interesting. It tells us something that how the path integral, at least in this simple case, is dealing with these singular spacetimes. It's projecting out certain data which would lead to singular solutions. All right, so now let's turn to a different question. So we've spent most of this talk thinking about the cylinder amplitude, the simplest thing you can do in de Sitter space. But now here's a problem. How do we handle other topologies? So the issue is that global de Sitter space in 2 dimensions is the only globally Lorentzian non-singular spacetime with R equals 2. The only one available to you that satisfies, again, these boundary conditions. So what else should we include? So let me tell you, I'm just going to erase the boards here. Let me tell you a clue that's going to lead us to how we should think about the other spacetimes. The natural place to start, the other kind of configuration in de Sitter space, which is not globally Lorentzian, but nonetheless is well studied, is the Hartle-Hawking spacetime. So a clue about how to deal with more general topologies is Hartle-Hawking. Geometry. Great. So let me draw a few pictures. I'm going to draw the complex time plane. We're going to have I pi over 2. Okay. So let me draw this down here, minus dt squared. So this is the usual global de Sitter metric in 2 dimensions. And there's a way of relating this to the Hartle-Hawking state. So the Hartle-Hawking state looks like, its upper half looks like global de Sitter space, but its bottom half, it's glued to a Euclidean hemisphere down here. The way of thinking about this is that you can take the time contour, so the Lorentzian part of the time contour runs along here. And then you can have the Euclidean part of the time contour run along here, from I pi over 2 down to 0 and then off to infinity. So if you take this metric and you take t and think about it as being complexified, then if it runs along this contour, it'll analytically continue the spacetime to something that looks like the Hartle-Hawking state, which gives you the gluing between this Euclidean cap and this Lorentzian throat. Now, there was a very beautiful idea that was, okay, so one last thing about the spacetime before I erase it. This satisfies, at the risk of you not being able to see it, but I'll say it in words, r equals 2. So it's a complex metric, but with this contour of t, it still satisfies r equals 2, so that's good. All right. So Maldacena has this interesting idea in 2003, or he leverages a very interesting idea, that there's a natural deformation of this contour. So the natural deformation of this contour is, let me get some other chalk, some green, is where you can take the contour and you have to start at I pi over 2, that's one of the fixed points, but now you can take it along this line, and then at infinity, maybe it'll dip down to 0 at some deferred time. And this is like taking t to be rho plus I pi over 2. And what does this spacetime correspond to? It corresponds to the Euclidean, the minus signature Euclidean ADS disk. And the coordinates are, let me write it out, ds squared is minus d rho squared plus sinh square root of rho d theta squared, and phi is I pi over 2 pi cos of rho. So what's going on? The continuation of this contour gives us minus signature Euclidean ADS. So it looks like the Euclidean ADS disk was a minus sign up front. And it gives us a dilaton that has a complex asymptotic value. So in the parlance of the Euclidean ADS theory, this is like saying that we have that the temperature, the effective temperature in this ADS theory is like 1 over I phi minus epsilon if you take care of the I epsilon. So it's like it's some imaginary temperature that's actually a bit negative.
What happened with the scalar conversion?
Great, it's still 2. And why is it still 2? The reason is that in minus signature, Euclidean ADS geometries have constant positive curvature. And the reason for this is that the curvature is cubic in the metric. So if you consider something that's negative curvature, but you use the other metric signature, then you still have r equals 2. So that's the key trick that allows it to work. So what does this suggest to us? So the way that Maldacena used this in the 2003 paper is that it tells you that certain types of correlation functions in Euclidean ADS in all minus signature can be related to correlation functions of, for example, a Hartle-Hawking state in Lorentzian de Sitter signature, like cosmological correlators. The way that we're going to exploit this is that this gives us a suggestion of how to deal with the higher genus contributions in de Sitter and JT, which is that how do we generalize this to n boundaries or some number of future boundaries, some number of past boundaries in genus G? So here's the proposal. The proposal is number 4, that higher genus contributions to de Sitter S matrix elements may most naturally be expressed as all minus signature Euclidean ADS metrics, and also in this case with complexified dilaton. Let me spell this out. So what's the picture? The picture is that in Euclidean ADS, we know how to construct these smooth spacetimes, which look like this. Okay, just draw one more. Maybe they have some holes. And we have temperatures beta 1, beta 2, beta 3, say beta 4, and beta 5. So this we can construct as a non-singular, constant negative curvature Euclidean ADS solution. So the idea then would be to consider these Euclidean ADS2 solutions in minus signature so that they have R equals 2. And then to take the following to continue their beta. So if you want to have the beta correspond to a future boundary in de Sitter, you let it correspond to 1 over I 5 future minus epsilon. And the beta in the past would correspond to 1 over I 5 past minus epsilon. So what you'll find is if you impose this is that you'll find spacetimes which satisfy both R equals 2 and will also satisfy the de Sitter boundary conditions because of the fact that we've complexified the temperature. That ends up organizing such that we will satisfy the boundary conditions. Great. However, here's what we've really done here, and let me try to say this a bit more conceptually, is that good. So really what we've said here is that the contour of there is a relationship between the moduli space of solutions of constant negative curvature Euclidean ADS spacetimes and complex spacetimes that are smooth, satisfy R equals 2, and have the globally de Sitter boundary conditions. So let me write this in the following way. These geometries, in other words, provide a domain of integration for the de Sitter JT passenger.
But just a question about this, if beta are imaginary, are complex, or
yes,
imaginary, and so they are not the periodicity in theta. And theta is real, right?
Yes.
So they are. What's the period? They are no longer the periodicity in theta.
Oh, so even in Euclidean ADS JT gravity, you can have the betas be whatever you want. They're not obligated to be like 2 pi or something like this. So when you have general asymptotic boundaries, you can fix the asymptotic betas, and they have no periodicity condition.
So are they related to the geometric data, to phi and sin theta, etc.?
Yeah, so it's like fixing phi. It's related to fixing phi basically. It's fixing the asymptotic value of the dilaton. Sorry. So let me maybe write this out. So what we've done so far is that we've thought about a path integral. So this is an integral over, for example, de Sitter metrics. So this is highly schematic, but I just want to make a conceptual point, which is morally like this. So we've been computing a path integral here. We wanted to know what are the space of metrics that we should integrate over in dilaton. And the answer is that we now have a proposal of a moduli space of metrics, which are complex metrics, but they satisfy R equals 2. After we've integrated out the dilaton, we have to satisfy R equals 2, and they also satisfy the de Sitter boundary conditions that we required. So that's good.
And do they satisfy the conservage with them?
Good. So, well, maybe one thing to say is that because we're not coupling to matter, there's no issue here. But let me defer that question.
So why you have to satisfy everywhere too? I mean, just because it's a constraint, because they can be on shell, off shell, right?
What's that?
They can be off shell in principle. So why you insist on this satisfying everywhere too?
Well, because there's still R equals 2. So what it means to be on shell, and okay, so R equals 2 is Lagrange multiplier constraint, but there's still a moduli space of solutions which are mostly off shell. The only on shell solution is global de Sitter, where phi in the past equals phi in the future.
Yes, but why you cannot sum over metrics that don't away equal to? That's because it's a constraint of certain type or what?
Well, yeah, the idea is that the picture is that you integrate out the phi first. You integrate out the Lagrange multiplier, and that restricts you now to a domain of path integration, which is only metrics.
Yeah, but from a standard quantum field theory point of view, this would be just quantizing a sector of it, right? Because it's some part is on shell, some part is off shell.
No, but it's not on shell, it's a delta, it's function of delta in the integral.
This
Because
in general is not on shell, but he restrict himself to.
On shell and off shell is a concept that you apply when you have, say, quadratic integral.
Yeah.
A Gaussian, right? And here it's not a Gaussian, you have e to the I phi times something, and you integrate in phi, that's a delta that is a quantum constraint. There is no such thing as off shell, right? If you integrate phi from minus infinity to plus infinity.
So there's a separate computation you could imagine doing where you don't integrate out phi. I mean, you could imagine trying to do something both with phi still in play and field still in play, but the natural thing to do, as you said, is to integrate out phi first, totally integrate it out. And because it's linear in the exponential, it will literally, at the quantum level, as you said, tell you that you have to be R equals 2. Okay, but let me maybe make one last remark before concluding, which is that, okay, good. So here's a basic question. Is there some relationship? So something that you might expect, I'll put a question mark here, is if you thought about some integral over a different domain of, let's look at the metric over Euclidean ADS minus signature e to the minus Euclidean ADS and minus signature G. So you might think that a recipe is the following. What I should do is that we already know from the ADS version of the story how to do the path integral for Euclidean ADS JT. What I could try to do is that I could take that path integral and I could do a change of contour of the domain of path integration into this other contour, like go back to the Lorentzian segment or go back and forth, and impose these complex dilaton boundary conditions. Therefore, you could ask, is there a sense in which the de Sitter theory is actually kind of a contour deformation of the Euclidean ADS theory? This might be what his guess is. In fact, indeed, the basic picture that one had in this other paper is that if you want to consider quadratic fluctuations around a saddle, you can look at Euclidean ADS, in certain cases maybe coupled to a scalar. You can go to the de Sitter picture and you can learn about correlation functions. So the one last lesson that I want to explain is that this actually is not strictly true. And you find there's one last ingredient in the dictionary, which I don't have full time to tell you about, which is that the measure in the de Sitter theory is not actually exactly equal to the measure in the Euclidean ADS theory. In other words, this thing we've said about the things that we're integrating over, the metrics, that's about the domains, but it doesn't tell you that the metrics have to be the same. And let me tell you quickly what the difference is. In this case, it ends up being the Fathian, roughly speaking, of the Weil-Petersen symplectic form. That ends up being roughly what this measure is, up to some subtleties. In this case, one can show that it's actually Fathian of minus the Weil-Petersen bond, symplectic form. And you might think that that's a sort of trivial difference, but this gives you minus signs which depend on the number of boundaries in the genus of the spacetime. And these minus signs are actually essential to give you a positive definite inner product on asymptotic states, to give you a projector as opposed to minus a projector, and to give you these other features of not exactly unitarity, but isometricity. So there's again this additional subtlety actually about the measure itself of path integration, which I don't have time to tell you about. So let me make one more remark and then I will summarize. The one last thing to say, it was a question earlier about how this relates to matrix integrals. The short answer is that if you take the Stod-Shanker-Stanford matrix integral, there's a slightly different spectral curve. That all of the de Sitter amplitudes obey a topological recursion, but with respect to a different spectral curve. And I'll make one quick comment about what's going on. There's the parameter in the matrix integral goes like e to the s naught. This is in a double scale matrix integral. So e to the 2s naught is like a proxy for n squared in a double scale matrix integral. Turns out that in the de Sitter case, that the thing which appears is actually I times e to the s naught, formally speaking, like in the topological recursion. This is like having a string theory with pure imaginary string coupling. And that would be like having e to the minus e to the 2s naught, which is akin to minus n squared. So again, this is all formal. I mean, I'm just saying there's a topological recursion. So how seriously you should take this is not so clear. But let me make a remark. There's a nice paper by Hartman and Enos and Strominger about Vassiliev gravity. The proposal that the ON vector model, if you take n to minus n, would be dual to consider Vassiliev. What they're basically saying is that if you have in a vector model, the number of effective degrees of freedom goes like n, they're suggesting that you should take n effective to minus n effective to go from an ADS type model to a de Sitter model. For a matrix model, n effective is like n squared. That's the thing that shows up in fat graphs. So here it's a bit like taking n squared to minus n squared. I don't know quite what to do with that observation, but I'll leave it as a kind of cute suggestive remark. So in summary, we've developed a framework for, I told you about it in 2D, although we're now understanding how these lessons generalize to 2 plus 1 and 3 plus 1 for de Sitter, for the de Sitter path integral. And what we're working on is moving up in dimension from these nice JT computations to 2 plus 1, which is harder, and then 3 plus 1, for which we can say less, but can still say something. And I think that I'm happy to answer in the questions, but progress in these higher dimensional settings is underway, and I think that it provides some exciting avenues for explorations of quantum gravity and cosmologically salient spacetimes. So thank you so much for your attention.
In fact, actually, a question related to what Gaston was asking. This delta function arises if you integrate phi from minus infinity to plus infinity pointwise. Yes. Is that the right range for phi, or do you have to limit phi to be positive?
Yeah, no. So if you were to consider JT gravity, so one way of reasoning about where it comes from is if you imagine it as a compactification of like a near-Nari solution, for example, in 4 dimensions, then the field corresponding to the dilaton would have to be positive from that compactification. But then also the higher genus, there wouldn't really be any higher genus spacetimes. But if you view the de Sitter JT theory as salient in its own right, like we're just going to define it in this way, which is akin to the ADS theory, then it's sensible to go to infinity. The other thing to say is that for reasons that I don't quite have time to explain, this, even though this looks quite different than higher dimensions, and there's a way in which this directly maps onto computations you would do in 2 plus 1 and 3 plus 1, where there are, for example, in 2 plus 1 gravity, maybe most familiar, there's, if you do a quantization of Chern-Simons, you have to be careful about the measure and usual and so on, because we're thinking about gravity as opposed to Chern-Simons gauge theory. But regardless, there's a Lagrange multiplier constraint that shows up in the quantization, which is one of the components of the gauge field, and it plays a similar role as phi. But anyway, let me maybe not delve into that for the moment, since it's a definition of the theory.
Just a question about this difference between the measures. As you said, there's an extra minus sign that goes into the de Sitter case.
Yeah.
Is it understood how the minus sign actually contributes, like through some kind of eta invariance?
So through what?
Eta invariance. So
let me make some remarks about.
Can you make a general statement, like it's more explicit between the measures on the PS and on the PS?
So I don't know what the general story is, but let me tell you.
The fixed topology, for example.
Yeah. So let me tell you 2 features though that I do understand. So I don't know how this relate to eta invariance or coupling matter fermions or whatever it is. But the 2 things to say is that if you want to get positive definite inner products in asymptotic states and unitarity amplitudes even in subsectors, that the minus sign is essential. And there's a second thing which it does, which is more mysterious, which is that if you look at the contributions for an S matrix element by summing over higher genus contributions, it forms an asymptotic series. And what the minus sign does is it gives you an alternating sign asymptotic series, which puts the Borel singularities on the negative real axis, so that this thing is now Borel resummable, which is not a feature of the Euclidean ADS theory. So that's, I don't know what to do with that information besides it tells you something about the lack of ZZ instantons, at least nominally, in a naive UV completion of the theory in the sense of resurgence. But it is at least a feature that this leads to alternating signs in the genus expansion. So let me just mention that as a feature.
And with this minus, you say that the S matrix that you get obeys unitarity. So it's
one has to be careful because it's not. It's the, for example, the 1-to-1 amplitude in the subspace of initial conditions that don't lead to a crunch is equal to 1 basically because it's a projector, but it's 1. But if you do it the other way, you would get -1, for example. So in other words, this quantity has to be a positive definite quantity because it's equal to VV dagger. But if you want that to be a projector as opposed to minus a projector, for example, then this minus sign is essential for that. But actually, the more interesting quantity I would say is that the inner product itself on asymptotic states, if you want that to be positive definite, as opposed to negative definite, then the signs actually are essential for that.
Can you explain, like, maybe an example where how that happens? How this minus sign give you positive inner product?
Yeah. So
Or
well,
if it takes more time, I can also.
I mean, it takes more time, but there's the most illuminating thing to say essentially is that the measure that you get is not d alpha squared, but minus d alpha squared. So let me explain to you everything. It's like a 5-minute computation.
Okay. But maybe ask a more kind of a broad question. So do you expect this equality once you substitute the correct measures, this relation actually holds non-perturbatively or just perturbatively?
So this actually holds. So one can make sense of this path. Also, in other words, if you do the replacements that I said,
Yeah.
it holds to all orders in the genus expansion. So that's non-perturbatively in the sense of a genus expansion. But you could also ask more ambitiously about doubly non-perturbative amplitudes. For those, I have no idea, except that the resurgence picture would suggest to you that naively there aren't really ZZ instantons in theory. But even the status of the Euclidean ADS, doubly non-perturbative sector is a little bit ambiguous for a number of reasons.
How much of the story survives when you add matter?
So if you, for example, consider so let me make one remark on that. So something that we're computing at the moment in higher dimensions, we're even coupled to matter like scalar, for example, is you might ask if you take the Hartle-Hawking state, maybe with a scalar, so combined with a bunch of APs, and you look at the inner product of the Hartle-Hawking state with itself at one loop level, then one thing that you might expect to get is the one loop sphere partition function. So I'll just make one quick remark about this. So a picture that you might have is that if you were to take, so this is at the level of like picture analysis. This is an idea which sort of goes back to Coleman. If you were to glue together a Hartle-Hawking state with itself, there's a question if you did everything at one loop, including we're careful about the norm on asymptotic states, you could ask, do you get a sphere partition function to one loop? So Z sphere at one loop. Now, one observation, which is that famously Polchinski did a calculation of the sphere partition function, or I guess the log sphere partition function, and what you find essentially is that that the sphere partition function itself actually has factors of I in it, which depend on the number of dimensions you're in. But in fact, if you do, what we're finding by doing an analysis in 2+1 and 3+1 dimensions is that if you follow these procedures, even in the presence of the scalar, and we're still trying to understand this, what you find actually is that the answer that you get is so let's say sphere of Polchinski, which contains these factors of I. The inner product that you find when you do this carefully is actually the absolute value of this. The factors of I go away. So there's something you would expect that the inner product of a state with itself should be positive definite. And one nice thing is that one can use these techniques, ostensibly even in the context of coupling to matter, perturbably, to get answers that make sense and that kind
This
of.
is the same I issue of the last Maldasenas paper.
Yeah, so the Maldasenas paper, what he showed was that if you put in a world line, you get these other factors of I that would cancel out the Polchinski factors of I. However, if you put in two world lines, then you get more factors of I. You might be able to argue actually that two world lines have an instability to combine them to give you a single world line, but nonetheless, you might ask that this be true in the absence of a world line, and it turns out that actually. So anyway, the thing that Maldasenas was computing was not this, but he was just computing the sphere partition function, like the de Sitter entropy. But what I'm saying is that if you compute the norm, the thing that Christian and I have been working on is that if you compute the norm of the Hartle-Hawking state, you get the absolute value of the thing. So it actually doesn't have the factors of I.
Maybe a related point. So I think this one is more naturally just positive and well defined, but the sphere partition function itself actually suffers from log divergence. I mean, there's ambiguity because of that. We have massless matter.
Yeah.
How do people deal with that?
I
mean, here there's no problem because there's you just talked about it before.
Right. So there's different, yeah. So I mean, there's an ambiguity, and you have to choose some.
Sorry? Just divided by the gauge group volume. No, yeah, okay. Okay. Talking about different.
There's a different number, yeah, so that I don't have much to say about, but that's a separate issue. Yes.
So here you've done a very global de Sitter space approach, but you
Yeah.
could also have, there's an idea that maybe everything should be done in the static patch. That de Sitter quantum gravity lives in the static patch, in which case you might have expected a theory like that, there's a finite dimensional Hilbert space that corresponds to the number of states being related to the entropy. Do you see any of that here?
So let me make two comments about that. So one is that there's a proposal that so if you think about a static patch solipsistic point of view, you might propose that the static patch is dual to a single quantum mechanical theory, like a unitary theory, for example. I mean, it depends what the proposal is. It's most naturally an open system is the problem, but there's various ways of getting around that. But there's a different question that you said. I'm going to focus on a different aspect of the question, which is there's a folklore, roughly speaking, that the Hilbert space dimension of de Sitter quantum gravity should be finite dimensional and related to the exponential of the de Sitter entropy, roughly speaking. So here's a fantasy about how that could play in with this, which de Sitter JT is not smart enough to tell us about, unfortunately, which we're too weak and feeble to do in higher dimensions. But the thought is, suppose, okay, so let me tell you about one quick generalization. If you instead consider de Sitter JT coupled to defects, so you can add in defect operators in various ways. These allow you to have a crunch on specific values of negative alpha squared that correspond to the defect angle. So what you find then is that you don't just get a projector, but you allow bounce geometries to sail through, and you can have certain crunch states at specific values of the cone angle because you can end on a defect. So the more general picture is you might imagine the following. There's naively in de Sitter quantum gravity an infinite dimensional asymptotic Hilbert space. But maybe in fact that any mild perturbation is going to lead to a crunch geometry. And maybe for some stringy reason that we don't know, there's certain sort of a discretum or there's a certain set of states of brainy or whatever configurations on which we're allowed to end. So in other words, maybe it's the case, again, there's this distinction between the bulk Hilbert space and the boundary Hilbert space. Maybe the bulk Hilbert space is actually related to the de Sitter entropy. And that roughly speaking, that the bulk Hilbert space is finite because there's a finite number of configurations that are allowed to sail through in the S matrix. So in this case, we saw a reduction from an infinite dimensional Hilbert space to a smaller infinite dimensional Hilbert space in the sense that there's a natural injection, but not surjection from one to the other. But more dramatically, you might imagine that you can go from an infinite thing to a finite thing. That's a fact. I mean, that's
So you're saying there's a kind of projection to a subspace that is non-singular, for which there will be finite.
or which is singular in the right kind of way. Okay, that's just a speculation.
Yeah, quick question about that bulk Hilbert space. So you are losing, right, half of these half the lines. You only have this half line. So how do I interpret the fact that I'm also then losing phi as a adjoint operator? Right? It's conjugate, right, to this p or something like this.
So
so I can no longer label my states maybe with phi in the bulk.
Well, indeed. So in the bulk, you have to label them with a positive value of p, and you have to basically deal with, as you say, the subtleties of quantum mechanics on the half line.
Yeah.
Now, in the canonical quantization picture, there's this nice recent paper by Maxfield and Held, which in fact deals with these subtleties. So I recommend looking at that. But when we did this, so this work was based off of a number of papers that were written with the various authors up there over the last 5 or 6 years. So we didn't do it that way originally, but it's indeed nice to see that in the canonical formulation, it is like the quantization of particle in the half line, at least the bulk.
So there's no S-line computation that you're not labeling states.
Okay, maybe let's thank Jordan again.